Welcome back to Wood Engineering. I'm Jeff Rochko from Carleton University, and in this video, we are going to start a series of videos doing the most epic complete beam column design example ever. We are going to go through every step. We're going to look at how do I pick my sections. We're going to look at all the load combinations. We're going to include an uplift combination, which acts opposite to the other loads. We're going to include shear notch cutouts. We are going to include bearing capacity, deflection, and of course, we're going to look at the interaction between axial load and moment in both directions. So it's going to take a while, but basically this should give a good overview of the complete design process for quite a complex beam column design case, sorry. Okay, so let's just dive right in. Okay, we have a glulam column here shown on the right. We have kind of an architectural detail that the architect would like that has to do with the way that the windows are created. I mean, I'm not an architect, so this is probably a stupid detail, but it gives us an opportunity to do a check on a compression side notch. So we have kind of a fancy glulam beam column here, and it's a beam column because it has loads from above, the dead load, snow load, and a wind uplift. And it also has lateral loads, which in this case are coming from window mullions, which are the horizontal members of windows, of a window frame that are carrying basically the load from the windows to the beam column, which then carries those loads to the rest of the structure. I have CLT floors at the bottom and the top, which are restraining the movement in this direction and in the out of plane direction. So laterally and out of plane, and same at the bottom. And I'm also saying that where these window mullions are, they are preventing out of plane deflection. So it can't move out of plane like this. And we also have an eccentricity on our load. So we have two different effects of moment that we need to consider. One being, of course, the direct moment caused by these lateral forces from the wind, these ones. And we have an additional moment that's caused by this load here being eccentric relative to the center line. So basically what I'm saying in this description is that there is the load that is being carried from above, and basically just on the above side and not on the below side is located at the center of this top face. So this is the top face. That top face is not as wide as the entire beam. It's not as wide as this because of those cutouts. And due to geometry, I mean, this thing is obviously stepping in at some point here, and there's something sitting on top in the real structure. That load is centered at the center of that top face instead of at the center line of the entire member. So it's not located here. It's located off from that a little bit. Okay, so we're going to have to determine what that eccentricity is. You know, this distance here is going to be our eccentricity E. And of course, we don't know what that is right away because we don't know the size of our column because we haven't chosen a column yet. So we have to choose this column, this beam column, and that's going to define how deep this notch is. It's going to be 20% of the total depth. And based on the size of that column, we're going to have a different eccentricity. And that eccentricity is then in turn going to affect our moments. So tons to consider here, and we're going to have to go step by step by step, of course. The geometry of the notches is given, as I said, as 20% of the depth is the notch depth, which is less than the 25% limit. And we have a 0.4 meter length on that notch, so we're going to be able to calculate our EC. And I've given the size of the CLT floor because we're going to need that when we calculate the EC, because remember that the length of the notch is from the edge here to the end of the notch cut. And we have a 3 meter long beam column, and the window mullions are spaced at 1 meter basically. Okay, so we're going to make some simplifications when we go through the design of this. And we're going to have to be very careful with how we consider all of our loads. Okay, so as I said, a column is supported in the out of plane direction at the window mullion load location. So that's here and here for out of plane, and it's supported in both in plane and out of plane directions at the CLT locations. Okay, and we're doing dry conditions because I think we have enough to consider here in the design, and we're going to use spruce pine glulam, spruce pine 20F EX glulam, so we don't have to choose the what kind of material we're going to use. Okay, so we're 5 minutes into the video, haven't even started the actual problem. Okay, so I'm going to start with some initial thoughts of how we're going to approach this challenging problem. Okay, so as I mentioned, the load combinations are going to change depending on which size we choose because of the eccentricity of the top vertical loads. I already mentioned this eccentricity between here, between here, this location and this location. This eccentricity is going to cause a moment, and the size of that moment is going to change depending on the size of the member because the eccentricity is going to change depending on the size of the member. So how do we even get started? So I mean, we can't. How do we choose a member size if we don't know totally what the loads are? Well, basically what we're going to have to do is make some conservative, I would make a conservative assumption of the size of the beam and the eccentricity, and then circle back and see then what the resulting eccentricity is going to be after we choose a better size beam. So first of all, we're going to have to get some idea of what the loading is going to look like so that we can pick some kind of rough idea of a section size. So these are the loads. If you recall, we got a dead load. Okay, so we got dead load, snow load, we have a wind uplift, which is the vertical load, and we have the lateral wind load, which is 30 kilonewtons at each location, at each window mullion location. So let's try to figure out what are the kind of approximate axial load after we factor and approximate moment and shear after we factor so that we can figure out what an appropriate size is going to be. Okay, so let's take a look. So first I'm going to look at approximate loadings here. Okay, so I'm not going in detail here. I'm making assumptions. I'm not considering my load combinations properly. I'm just making an educated guess about which load combinations may govern, and I'm trying to make conservative assumptions for all of them, just so that I can get like basically an upper bound idea of what the loads are going to be. So for example, PF approx, right, might be probably, since we have dead and live, so I'm talking about the axial load on the column here, since we have dead and live load and the wind acts counter to that, let's just look at what's the maximum kind of overall compression load that we're going to get if we just do 1.25 dead plus 1.5 times snow. And if we do that calculation, we're going to get 487, 0.5, too many sig figs, but 488 kilonewtons. Okay, so that gives us kind of a rough idea of what my maximum compression load is going to be. Okay, that's probably which load case would govern. Okay, so now let's make some kind of conservative assumption about eccentricity. Maybe I want to first see kind of what are going to be the strengths of these kind of members and choose a very conservative member first so I can get a very conservative eccentricity. To do that, I'm going to go to the selection tables, and I'm going to first go to this one. Okay. Okay, so here is glulam selection tables. Now, this is not the regular selection table. The regular selection table we find in, for compression, we find that in section, let me see, which one is compression? Usually we come to this compression members one if we want to check column size, right? But if we go to the if we go to the tables in this section, the compression member section, and we go to glulam, you'll notice that we don't have the grade of glulam that we're working with. We have 12 CE. This is a bit tough to see, admittedly. We have 12 CE here, 16 CE, and that's it. We don't have 20 FEX. Okay, so how do I calculate the compression strength of this grade, which is not commonly used for columns? Well, in the standard, there is provided a section, so that's bending members is 2, compression members 3, tension 4, 5 is combined loads. And what this does is it doesn't give like a beam column table per se, but what it does give us is a table that shows us, if I go to the right table in this section, this page here, what it does give us is it gives us column selection table for beam type grades. Okay, so in this chapter of the wood design manual, I can find a table that gives me compression strengths, compression parallel strengths for 20 FEX glulam, which is typically a this is a beam grade. Typically this is something that you would use for beam, but if you're designing a beam column, then this is a grade that you would conceivably use. So you can't find the compression strengths in the compression section. You have to find them in the combined loading section. Okay, so here I have 20 FEX. Now I wouldn't use 20 FE because that one's unbalanced, right? As we've talked about many times before, and that would not be a good choice for a column to have an unbalanced section, because then we're obviously going to be probably inducing some bending just by applying axial load. So we want to use the balanced section 20 FEX. So this is the grade that we're using. We just said that the axial load is about 487. We got to remember as well that we are dealing with bending as well. So I can't just use something that has exactly 487. I have to pick something that is quite a bit bigger than that. You can see that none of these values work. Let's say we're looking at the PRY because that's weak axis. So right now I'm not considering at all my support conditions or anything. I'm just saying my beam column is 3 meters long, and I have about 475, 485. So this is not going to be very good either because I have to get all the way up to 475. So let's continue. Okay, this one's 475, but I got to go to 3 meters. So this is PRY is weak axis buckling, PRX is strong axis buckling. Okay, so that's probably not far enough. So let's just like come all the way down here and yeah, let's say that, you know, I'm using kind of one of these sections here. This should have probably plenty of strength, right? If I was at like 1,000, 1,500, then this would be basically my depth of my section, 380. Okay, so let's assume something like that to start. So we went with about 380. So let's say it was about 400. So we're going to make a conservative assumption for eccentricity, because we need the eccentricity in order to determine what's the applied moment so that we can actually pick some kind of halfway reasonable section. So we've only looked at axial load so far. So let's say that our D of our member, the depth, is somewhere around 400. We said 380. Let's just round to 400. We're doing everything approximate here. What's the E going to be if I have 400? Well, let's just look at that geometry briefly. This is basically what the geometry looks like approximately. Okay, we have the center of the member, which is at, right, 0.5 D. Okay, so that's what we're going relative to when we calculate our eccentricity. And this here is 0.2 D, right? Therefore, this distance here is 0.8 D. Okay, so we said that the load is coming at the center of the top flat surface. Okay, that was given in the question. So that means that it is going to be halfway 0.8 D, which means it is going to be 0.4 D from this edge. So the load is 0.4 D from the edge. the center is 0.5d from the edge, so the distance between those two is the eccentricity. Therefore, the eccentricity is always going to be 0.1d. Okay, so that holds no matter what size the section is. So this makes it easy for us to always calculate our E. So therefore our E, let's assume that it's approximately 40 millimeters and move forward. Okay, so now that we have that, we can calculate the moment and the shear. Okay, so my moment is going to have two different components, and I'll look at these in a bit more detail later. But we basically have one component of the moment that is from the lateral load. So remember, I have two lateral loads like this. They're each 30. So my moment looks like this. And since this is 1 meter, 1 meter, 1 meter, this is also 30 kilonewtons. And then the other part of the moment is from the eccentricity. And remember, the moment that is caused is the load times the eccentricity, right? So this is going to be P times E, which in this case is going to be the total P, which is, we said it was 488. We're going to multiply, that's kilonewtons. We're going to multiply that by 40 millimeters, so that's 0.04 meters. And we get 19.5 kilonewton meters. Sorry, this one is also kilonewton meters. Okay, and you know, those are actually going to typically act in opposite directions as shown here, but we'll consider that in a little bit more detail later. For now, just to get a rough estimate, I am going to just add this value to this value. Okay, I'm doing things super rushed. Now you could take more care at this point if you want. That's totally fine. Like, these moments aren't even in the same location, right? They're in totally different locations. Like the PE is at the top, and that moment 30 kilonewtons per meter is kind of 1/3 of the way down. But anyway, I'm just going to add them all together for now. I'm just looking for approximate moments so that I can pick an approximate section so that I can continue. So I'm just basically getting a first iteration, just quick and dirty. So this is going to be about 50 kilonewton meters. And the shear is going to be, oh, and I have to factor that because this is wind load, right? So I'm going to multiply that by 1.4 to apply a wind load case to it. You know, part of that load is not wind load, right? Part of that load is, well, this one was already factored, actually. This one was factored. So I should actually multiply this one by 1.4 here. So let's just fix that a bit. So this would be times 1.4 times 30 and 1.4 times 30. And so we're going to get 1.4, of course, is the typical wind load factor in our load combinations. So this is going to actually be 42. Okay, this one on the right was already factored. You remember we factored that number when we put it in. So this is going to actually be 42 plus 20, so it's going to be about 62. And the estimated shear is going to be 1.4, and our shear, our unfactored shear in this one is 30 kilonewtons. So we're going to get 42. Okay, these are all approximate numbers. Okay, the reason I'm doing it this way is just to give you an idea of kind of a an approach that includes like going from very, very rough to getting more and more precise as we go further and further down the problem. Okay, so what would be a good section for this? So remember we have, again, about 490 axial. We have 62 moment and 42 shear. Okay, so this was what we were using before, was the 380, 265 by 380. And that had a axial load resistance of about 1480 over 3 meters. Okay, not considering the lateral support conditions. Okay, and let's look at the, and this is 1560. And let's look at the shear and moment. So if I go to the beam selection tables now, I have again my correct stress grades. Okay, so let's look at the strength of this. Now these are just the 20FE stress grade, so 20FEX is going to be a little bit stronger. We're going to calculate the actual value later. So we had a 265 by 380, which is this one here. We're looking at spruce pine. So the moment resistance is 147, the shear resistance is 106. And the ESI is 12,500. We'll need that number when we calculate deflection, but let's just leave it out for right now. Okay, so if we take all of those numbers, okay, so we had okay, so from those tables, which we just looked at, these are the MR, VR, PR, and PRY. So we had, remember about our PF approx was about 490. So we're at about a third of that. And the moment that we estimated was about 62. And the V approx equals about 42. So you see we're about 3 times over on the moment and the axial load. There's a bunch of things that we haven't considered, like the shear notch, and we haven't considered lateral torsional buckling, and we haven't considered explicitly compression buckling. So basically what we get out of this is that maybe if we assume an eccentricity of about 40, we know that that number is likely going to be conservative. The true eccentricity is going to be below that. So all of that is just to come down and say, okay, so basically based on this, we're using up a third of the moment, a third of the axial force. So that means, if we're doing a simple interaction where we have a third and a third, then we have kind of a third of the strength left over. So I think we're pretty confident that our size, the size of our member, is going to be smaller than this. So that means this eccentricity value should definitely be conservative. So what I'm going to do from this point, but it's not crazy conservative. Like, it's conservative. Maybe we're going to get an E of between 20 and 30 or something like that. And there might be a bit more left over, maybe 10 millimeters, but also there's going to be fabrication tolerance and construction tolerance. So picking an E that's a little bit bigger than what I might technically have is not a big deal, but I think this is a reasonable value to choose. So now that we have this E, now we have a way basically to calculate our moments and confidently, so that we are pretty sure that we're going to have upper bound factored moments, and then we can do our load combinations. So I'm going to put a cut in here then, and in the next video, we are going to start with calculating all of our load combinations based on these values.